Hello everyone, myself Ankush Haldkar. This lecture is based on safety in dams and bridges. Safety in dams and bridges is of utmost importance to protect lives, property and the environment. Both dams and bridges severe critical functions in infrastructure and ensuring their safety involves rigorous planning, designing, construction and maintenance processes. Here are some key considerations for safety in dams and bridges. Safety in dams. Risk assessment. Before constructing a dam, a comprehensive risk assessment should be conducted to identify potential hazards, failure modes, and their consequences. Risk assessment in dams is a systematic process that evaluates potential hazards, identifies possible failure modes, and assesses the associated risk to ensure the safety and integrity of the dam. It involves evaluating various factors to make informed decisions regarding dam design, operation, and emergency preparedness. Here are the key steps involved in risk assessment for dams. Identify hazards. Being by identifying all potential hazards that could affect the dam, including natural events, example floods, earthquakes. Human-made events, example construction, accident, sabotage, and internal issues, example seepage, erosion. Consequence analysis. Determine the potential consequence of each identified hazard. This involves assessing the impact on human life, property, and the environment. If the dam were to fail, consider factors such as downstream population, infrastructure, and ecological sensitivity. Failure modes analysis. Identify the various failure modes or scenarios that could lead to dam failure. Common failure modes include overtopping, foundation failure, seepage, and structural failure. Probability assessment. Evaluate the likelihood or probability of each failure mode occurring. Consider historical data, geological studies, meteorological data, and engineering analysis to estimate the probability of each hazard scenario. Risk calculation. Calculate the risk associated with each failure mode by multiplying the consequences by the probability. This quantifies the potential impact on each scenario and allows for risk prioritization. Risk ranking. Rank the failure modes based on their calculated risk levels. This helps prioritize which scenarios should be addressed first in terms of risk reduction measures. Risk mitigation measures. Develop and implement risk mitigation measures to reduce the probability of high risk scenarios and minimize their potential consequences. Mitigation measures may include dam design, modifications, structural improvements, early warnings, and emergency response plan. Emergency Action Plans (EAP). Develop a comprehensive Emergency Action Plan (EAP) that outlines specify action to be taken in the event of a dam failure or high risk situation. Ensure that EAP is well communicated to relevant authorities and the public. Monitoring and surveillance. Implement a monitoring and surveillance program to continuously assess dam condition and detect any signs of potential failure. Monitoring can include instrumentation for measuring water levels, seepage, and structural movement. Regular review and updates. Periodically review and update the risk assessment, especially after significant changes in dams conditions, construction, or environmental factors. It's important to ensure that risk assessment remain accurate and relevant over time. Community engagement. Engage with the local community and stakeholders to keep them informed about the dam safety measures, potential risks, and emergency responses procedures. Public awareness is crucial for a coordinated response in case of emergencies. Regulatory compliance ensure that the dam complies with all relevant dam safety regulations and guidelines established by government agencies. Risk assessment in dams is an ongoing process that requires collaborations between dam owners, engineers, geologists, hydrologists, and emergency management agencies. By identifying and mitigating potential risks, dam safety can be enhanced, reducing the likelihood of catastrophic dam failures and protecting downstream communities and the environment. Design standards. Dam must be designed according to international or national standards and guidelines. Design considerations include factors like the type of dam, example, earth fill, concrete or rock fill, spillway designs and foundations stability. Design standards for dams are crucial to ensure the safe and reliable construction of these critical infrastructure elements. These standards provide guidelines, specifications, and criteria that engineers and dam designers must adhere to when planning, designing, and constructing dams. Below are some of the key standards and considerations for dams. International guidelines and standards. ICOLD, International Commission on Large Dams. ICOLD provides guidelines and standards for the planning, designing, construction, operation, and maintenance of dams. Its publications are widely recognized and used internationally. National standards. Each country typically has its own set of national standards and regulations for dam designs. These standards may vary depending on factors such as dam type, size, location, and the associated regulatory framework. Dam types. Different types of dams, example concrete gravity dam, embankment dam, arch dams, have specific design standards tailored to their construction and function. Next is geotechnical considerations. Design standards address geotechnical aspects including soil and rock machines, foundation stability, and seepage control. Proper geotechnical investigations are crucial to ensure a sound foundation. Hydraulic design. Hydraulic design standards cover spillway design, outlet works, and flooding routing. They ensure that the dam can safely manage inflows, floods, and reservoir operations. Structural design. Structural design standards focus on the structural integrity of the dam, including factors like materials, reinforcement, and structural safety. These standards are essential for concrete dams and other structural elements. Hydrological design. Hydrological standards specify how to eliminate inflows, design floods events, and determine reservoir operating rules. Accurate hydrological data is crucial for dam design. Environmental considerations. Modern dam design standards also emphasizes environmental aspects including fish passage, habitat preservation, and minimizing the ecological impact of the dam. Safety factors. Design standards include safety factors to account for uncertainties in materials, constructions, and loading conditions. These factors provide an additional margin of safety. Instrumentation and monitoring. Design standards often require the installation of instrumentation to monitor dam performance continuously. This includes sensors for water level, seepage, and dam movement. Emergency preparedness. Standards may outline requirement for emergency action plans (EAPs) and early warning system to respond to potential dam safety issues. Construction specification. Construction standards and specifications define the method and quality control procedures that must be followed during dam construction. Operation and maintenance. Design standards may include guidelines for ongoing dams, operations and maintenance to ensure the safety and integrity of the structure throughout its lifespan. Sustainability and climate change adaptations. Some modern dam standards address sustainability and consider the potential impacts of climate change on dam design and operation. Engineers and dam designers must stay up to date with the latest design standards and guidelines as they may evolve over time to incorporate new technologies, research, finding, and safety measures. Compliance with these standards is essential to ensure the safety and long-term functionality of dams, as well as to meet regulatory requirements and protect downstream communities and the environment. Emergency preparedness. A well-defined emergency action plan (EAP) should be in place to address various failure scenarios. It should include evacuation procedures, warning systems, and communication strategies. Maintenance. Maintenance and regular inspection are necessary to address wear and tear, erosion, and other potential issues. This inspection should be carried out by qualified personnel. Community awareness. It's essential to educate the local community and the dam safety, emergency procedures, and evacuation routes. Climate change adaptation. Consideration of the potential impact of climate change on dam safety is becoming increasingly important. Changes in precipitation patterns and increased variability may affect dam operations. Climate change adaptation in dams is a critical aspect of dam management and design. In the face of shifting climate patterns, increasing extreme weather events, and rising global temperatures, dams play a crucial role in managing water resources, mitigating floods, and providing a stable water supply. Adapting dams to climate change is essential to ensure their continued effectiveness and safety. Here are some key considerations for climatic change adaptation in dams. Hydrological modeling. Re-evaluate hydrological models and data to incorporate climatic change projections. This includes assessing potential changes in precipitation patterns, runoff, and stream flow, which can impact reservoir management and flood control. Reservoir operations. Modify reservoir operating rules and strategies to accommodate changing hydrological conditions. Adjustment may be needed to ensure water availability during periods of drought or to manage increased inflows during heavy rainfall events. Emergency preparedness. Update and enhance emergency action plans (EAPs) to account for climatic change include risks such as more frequent and severe storms, prolonged droughts, and increased flood risk. Ensure that EAPs are communicated effectively to downstream communities. Sedimentation management. Consider the potential for increased sediment transport due to intensified rainfall events. Develop strategies for managing sedimentation in reservoirs, as excessive sedimentation can reduce storage capacity and impair dam functionality. Seepage control. Evaluate seepage control measures to account for changing underground water conditions resulting from altered precipitation patterns, enhance seepage monitoring, and implement additional measures if necessary to maintain dam integrity. Structural resilience. Assess the resilience of dam structures to extreme weather events including increased wind loads, intense rainfall, and temperature fluctuations. Reinforce dam infrastructure as needed to withstand these conditions. Flood management. Reevaluate spillway design and capacity to accommodate larger flood events that may result from climatic change. Consider the need for additional flood control infrastructure or improved warning systems. Water quality. Monitor and manage water quality in reservoirs as climatic change can impact temperatures, regimes, and nutrient levels. Changes in water quality can affect aquatic ecosystems and downstream users. Ecosystem considerations. Recognize the importance of maintaining ecological flow regimes downstreams of dams, modify dams operation to support aquatic ecosystems and preserve biodiversity, particularly in regions with sensitive habitats. Community engagement. Involve local communities and stakeholders in the adoption process. Share information about climate change risk, potential impact on dam operations, and measures taken to enhance safety and resilience. Adaptive management. Implement adaptive management practices that allow for flexibility in dam operations and maintenance. Regularly review and update adaptation strategies based on new climate data and emerging challenges. Climate resilient design. For new dam projects, incorporate climate resilience into the design process from the outset. Consider climatic change scenarios, future weather patterns, and their potential impacts on dam performance. Safety in bridges. Safety in bridges is a paramount concern to ensure the well-being of the public and the longevity of these critical infrastructure components. Design codes. Bridges should be designed and constructed according to relevant design codes and standards. These standards cover materials, load bearing capacities, and safety factors. Design codes for bridges are a set of guidelines, standards, and specifications that engineers and designers must adhere to when planning, designing, and constructing bridges. These codes ensure the safety, durability, and functionality of bridges as well as compliance with legal and regulatory requirement. Design codes for bridges can vary by country and region, but there are several widely recognized international codes and standards that are commonly used. Here are some of the notable design codes for bridges. ASTHO LRFD Bridge Design Specifications. This is by United States. The American Association of State Highway and Transportation Officials ASTHO LRFD Load and Resistance Factor Design. Bridge design specifications are widely used in the United States for the design and evaluation of highway bridges. Eurocodes, European Union. The Eurocodes are a series of European standards that cover the design of civil engineering structures including bridges. Eurocode 2 EC2 focuses on concrete structures, while Eurocode 3 EC3 cover steel structures. Different parts of the Eurocodes deals with various aspects of bridge design. BS 5400, United Kingdom. British Standards 5400 provide design guidelines for steel, concrete and composite bridges in the United Kingdom. It covers various aspects of bridge design including materials, loading and construction. CAN/CSA S6, Canada. The Canadian Highway Bridge Design Code CAN/CSA S6 is used for the design, evaluation and rehabilitation of highway bridges in Canada. It addresses both concrete and steel structures. AS 5100, Australia. The Australian standard AS 5100 covers the design of road bridges and other related structures in Australia. It provides guidelines for the design of various types of bridges and their components. Indian Road Congress IRC codes, India. The Indian Road Congress has published a series of codes and guidelines for the design and construction of bridges in India. These codes cover a wide range of aspects from materials to foundation design. Japanese Industrial Standards JIS, Japan. Japan its own set of standards for bridge design which are published under the Japanese Industrial Standards JIS system. These standards cover material, structural design and construction practices. ISO, International Organization for Standardization. ISO standards relate to bridge, cover various aspects including bridge management systems, bridge inspection and bridge load rating. These standards are applicable internationally. International codes, example IBC, IRC. Some countries or regions adopt international building codes or infrastructure codes that may include a specific provision for bridge design. For example, the International Building Code IBC in the United States has section on structural design including bridges. Local regulations. In addition to a national or international codes, local authorities and municipalities have their own specific regulations and standards that bridge designer must adhere to. It's essential for engineers and designers to consult the relevant design codes and standards that apply to their specific project, location and the type of bridge. Additionally, these codes are periodically updated to reflect advances in engineering practices and materials. So, it's crucial to use the most current versions and stay informed about any revisions or amendment. Compliance with design codes help ensures the safety and reliability of bridges while providing a basis for regulatory approval. Regular inspections. Bridges need regular inspection to detect signs of wear, corrosion, fatigue or structural damage. Inspection includes should be established based on the type of bridge and its location. Maintenance. Routine maintenance including cleaning, painting and repairing should be carried out to prevent deterioration. Maintenance activities should be documented and tracked. Upgrading and rehabilitation. Older bridges may need upgrading or rehabilitation to meet current safety standards. This can involve strengthening the structure or replacing key components. Bridge management systems. Implementing a bridge management system helps prioritize maintenance and repairs based on risk assessment and available resources. Community safety. Similar to dams, communities around bridges should be educated about safety measures and evacuation plans in case of emergencies. In regions prone to earthquakes, bridges should be designed to withstand seismic forces. Retrofitting existing bridges may also be necessary for seismic safety. Seismic considerations in bridge design and construction are of paramount importance, especially in regions prone to earthquakes. Earthquake-resistant design practices aims to minimize the damage of bridges and ensure the safety of users during seismic events. Here are the key seismic considerations for bridges. Seismic hazard assessment. Before designing a bridge, engineers must assess the seismic hazard specific to the region. This involves studying historical seismic activity, fault lines, and ground motion records. Seismic hazard maps and probabilistic seismic hazard analysis (PSHA) are used to quantify the level of ground shaking expected at the bridge site. Design code and standards. Design codes and standards such as ASTO, LRFT bridge design specification in the United States or similar international standards provide guidelines for designing earthquake. E-resistant bridges. These codes specify seismic design criteria including response spectra, ground motion, parameters and performance objectives. Seismic design parameters. Engineers must select appropriate seismic design parameters such as the design earthquake magnitude and ground motion response spectra based on the hazard assessment. Structural analysis. Bridges are subjected to dynamic forces during earthquakes. Structural analysis using finite element modeling and other techniques is performed to evaluate the response of the bridge to seismic forces. Engineers assess the capacity of bridge components, example columns, beams, foundations, to withstand seismic loads and deformations. Ductility and redundancy. Seismic resistant bridges design often incorporate ductility and redundancy. Ductility allows the bridge to absorb energy during an earthquake without collapsing, while redundancy ensures alternative load paths if one component fails. Foundation design. Proper foundation design considered soil structure, interaction and ensures that the foundation system can resist seismic forces. Deep foundations may be required in some cases to reach stable soil or bedrock. Seismic retrofitting. Existing bridges that do not meet current seismic standards, retrofitting measures may be applied to enhance their earthquake resistance. Retrofitting can involve adding shear walls, braces or base isolators. Seismic joints. Bridge expansion joints and bearing must be designed to accommodate seismic movements and deformations. Seismic joints allow the bridges to move during an earthquake while maintaining its integrity. Post-earthquake inspection and repair. After a seismic event, bridges should be inspected for damage. Any necessary repairs or maintenance should be carried out promptly to restore functionality. Emergency response plans. Develop emergency response plans for bridges including inspection protocols and procedures for accessing and reopening the bridge after an earthquake. Public safety. Bridges owners and authorities must ensure public safety by posting signs indicating load limits and restrictions during and after seismic events, regular public awareness campaigns, and can also educate the community about bridge safety. Seismic monitoring. Some bridges are equipped with seismic monitoring systems that record around motion data during earthquakes. This information can help assess the performance of the bridge and inform future designs. Seismic considerations in bridge designs are essential in protecting infrastructure, ensuring public safety, and maintaining transportation networks in earthquake-prone regions. Collaboration between structural engineers, geotechnical engineers, and seismologists is critical to designing and retrofitting bridges that can withstand seismic forces. Conclusion: both dams and bridges are critical components of infrastructure, and their safety is a shared responsibility among government agencies, engineers, and the public. Regular maintenance, inspections, and adherence to safety standards are essential to ensure the continued safety and functionality of these structures. Thank you and have a nice day.